interest of time. And it is a pleasure. If you're ready, Amit, are you ready?
Yes, I'm ready.
Okay, great. So I'm going to go right here so you can see me. So it is a pleasure to introduce my colleague, Amit Sanyal, who is a professor at Syracuse University right now. And his journey has been very interesting. He came from a degree at the Indian Institute of Technology in Kanpur. He completed his MS in aerospace engineering from Texas A&M. And then he went ahead and got his PhD in aerospace engineering and also MS in mathematics at the University of Michigan. And I think that's around the time probably where we met at the conference. And then he did a postdoc at Arizona State University. And then he started a faculty position in mechanical engineering at the University of Hawaii, from where he went to the mechanical aerospace engineering at the New Mexico State University. And then he, from there, jumped to this great location at Syracuse, where he now is at the Mechanical and Aerospace Engineering Department at Syracuse University. He works on all sorts of control problems, but he's very excited about geometric mechanics, nonlinear geometric control, and continuous and discrete time Lagrange and Hamiltonian systems with applications to guidance, navigation, and control of UAS. And he's going to be talking to us today about this. He's an associate fellow of the AIAA. He's a senior member of IEEE and a member of ASME and SIAM. He has had funded research from NSF, NASA, and FOSR, and he co-founded a company called Acrobatics LLC, which is a startup company. Maybe we hear some of that. With that, Professor Amit Sanyal, welcome.
Thank you for the kind introduction, Ricardo. So today I just thought that I'll present more of my older research, because while I started creating this and I realized that over the course of the last 2 decades, there are a lot of threads that are connected in my research. So I might as well concentrate on research that is not too old, but not too recent either. But there are forays into recent research in the sense, in the recent, by recent, I mean the past 3-4 years. So with that, I'll get started. And I gave a general title to my talk, Thoughts and Ideas on Autonomy, basically for safe and reliable autonomy of aerospace vehicles. So in this talk, I'm going to go over an overview and then applications, some technical challenges, engineering science of autonomy, applications and impacts, and then integrating research ideas and future directions. So some of these future directions are already ongoing directions, but I'll just mention a few on that. So in terms of the applications, we know that robotic or autonomous vehicles include aerial, ground, water and underwater, surface water and underwater space vehicles. And, model-based control has been around for a long time, and they work very well in many cases. But over the last decade, at least, we know that uncertainties, as our systems have become more complex and we are looking at different real-world situations and uncertainties in all domains, we have vehicles that are faster, larger ranges of motion. So we need to be cognizant of all these uncertainties and then come up with control and estimation, motion control estimation schemes that are robust to these uncertainties. So applications, of course, are of course, we have several domains and we have several application domains. So several domains meaning aerial vehicles, space vehicles, trans-atmospheric vehicles, although I'm not going to talk much about the third category. And there are wide-ranging applications like exploration, transportation, infrastructure inspection, remote sensing, security, etc. So there are, of course, increasing requirements for autonomy in these applications. And actually, I just mentioned these applications. There are more details that I have been working on. For example, on the exploration aspect that I'll mention, on remote sensing, for example, for natural disasters like wildland fires, which I'm involved in current projects in. So these are things that there are different sorts of uncertainties, and we require like safe autonomous operations in these situations. So this is like just to mention that these include search, rescue, and transportation. And then you have any grand challenges, which are like exploration, engineering tools of scientific discovery, urban infrastructure, security aspects that where autonomous vehicles can be a game-changing technology. And of course, we have had these for some time, but with the recent advent of different kinds of machine learning or deep reinforcement learning schemes, etc., which I don't really get into much. I have had tangential use of those and experience with those, but I stick to the more fundamental aspects of system, theoretic aspects of stability and robustness in whatever schemes that I describe here and in my research in general. So coming to the technical challenges for aerospace vehicles, we have guidance, navigation, and control. That's how you'll see aerospace engineers refer to the process of path planning, the process of motion estimation and mapping, and then the process of feedback control. So these aspects, in particular, the navigation and control aspects, are often, I mean, these are the aspects that need to be really stable and robust to uncertainties. And of course, if you're doing all of these, I mean, the last two are usually in real time. Even guidance can be done in real time. Sometimes it is not. But in all cases, you're operating the vehicle in real time for an aerospace vehicle. So real time uncertainty estimation and control and robustness, stability properties are very important. Now, challenges that I've listed here are uncertainties in the dynamics, sensor noise, and constraints. These include onboard power processor and sensor constraints, which are going to affect control and navigation in the first two bullet points that I've listed here. And then under actuation and actuator constraints, which affect the guidance and control aspects. And although I do not have many slides, or maybe not at all, on network control of multiple vehicles, this actually couples navigation, control, and communication. So it's ongoing, very recent research that I've been doing. I do not have much in my slides here on that, but I'll refer to it towards the end. In particular, its applications for monitoring and remote sensing kind of applications. So safety and reliability, we look at nonlinear stability and robustness of the GNC schemes. And what works in practice is not necessarily something that is optimal. So optimality does not buy you anything. That's how I quoted this as saying. So if you have something that works and that is that's robust to disturbances, that's stable, that is repeatable, then you don't really care about optimality, because optimality depends on your index, your cost function. And it may give you different results with different choices of your cost function or index. So in aerospace vehicles, the first thing that I teach my students, my graduate students, postdocs, those who work with me, is that the dynamics evolves on a nonlinear state space, in particular manifold. So that's where the geometric mechanics comes in, and related to that, geometric estimation and control schemes. So you have 6 degrees of freedom for a rigid body vehicle, and you might have internal or shape degrees of freedom, which would be additional degrees of freedom. So there are 3 degrees for translational motion, 3 DOF for rotational or attitude motion, and then internal or shape DOF due to actuators, power. Um, if you have power units that are moving as well, that are attached to your vehicle, like, for example, electrodynamic tethering or tethers that also generate power in spacecraft by interaction with the geomagnetic field. Flexible structures also contribute to internal degrees of freedom, and these motions are assumed to be uncoupled or only weakly coupled in a lot of control schemes. So that's how I have displayed this in these blocks out here. You have an attitude dynamics model, attitude state estimation, and then feedback control that's limited or no coupling at all with the translational dynamics, and then the translational states estimation and control of translational maneuvers. In reality, though, they are strongly coupled due to different reasons, most important being the fact that for aerospace vehicles, unless you are looking at very maneuverable and costly vehicles, the actuators are fixed to the base body and they generate fixed direction of thrust. So if you cannot rotate your thruster in your body, then you cannot actually have independent attitude and translational dynamics because they're coupled through the actuation. Besides that, for spacecraft at least, we have gravity, and gravity plays a big role in coupling attitude and translational dynamics. That's true even in aircraft, of course, but we assume that gravity is only, and it's a good assumption that gravity is only in one direction. So you have some kind of a symmetry about the gravity direction when you're flying in a plane or in air, and you have just one single direction downward of gravity. So the coupling does exist due to gravity, due to non-conservative effects, due to control forces and torques from body fixed actuators, and internal degrees of freedom. So internal degrees of freedom is what I don't talk about much here. Interestingly, that's what I worked on primarily, using internal degrees of freedom during my PhD research a long time back. So that is actually even more complicated in terms of the dynamics. After that, I found that people are still finding it difficult to deal with rigid body vehicles, and multiple rigid body vehicles. So that's what I do mainly. But internal degrees of freedom do play an important role in coupling attitude and translational dynamics. And that could be even flexible due to flexibility of the structure. Sorry, I think I went forward too quickly. So the effects of coupling are these, the coupling effects due to these different influences are often not known precisely. And if you assume that it's uncoupled, then it'll not be robust to these effects. In some cases, like I mentioned here, when the translational motion is, the energy in the translational motion is much larger than rotational energy, then the uncoupled approach works one way. So it works one way in the sense that the translational motion affects the attitude motion, but not the other way, because the translational motion has so much more energy than rotational motion. So talking about sensor noise, that's another thing that is usually we use simple models in estimator design. And you can have these simple models, and you can create an optimal, quote unquote, optimal estimation scheme based on these simple models, like extended Kalman filter, for example. However, that's not going to be robust, and that's, of course, the EKF is known to be even unstable, or it lacks guaranteed stability, let's put it that way. So you are not guaranteed that you'll have stable convergence. And here I show a sun sensor with its very non-Gaussian noise distribution with lobes and varying bias along the sensor plane. And any sort of simplified model like additive white Gaussian noise does not work well here. And in many cases, your sensor is evolving over time, and the noise distribution may be a slow variation, but that too changes over time. So in my research, I have primarily used deterministic methods because they're more robust, and I don't care about optimality, as I mentioned earlier. So deterministic works very well. So what works in practice is, and I tell my students this, that it's good theory that leads to good practice. So what works in practice, why change it? And of course, we have constraints on power, onboard processors and sensors, although these are becoming better and better as year to year. And we can see that some of these sensors nowadays can do, have inbuilt schemes based on CNNs that can detect obstacles in real time and move out of the way. So that's actually the perception problem, which I think is where computer vision has made a lot of progress, but I'm not going to really focus on that. But that's something that I have used and continue to use. So there are some aspects of that is useful, although I don't rely on it entirely in feedback loop because again, uh, there are problems with those perception schemes. So in terms of the under actuation, I have I think I'll just go over this quickly. We have, as I mentioned before, this is for most aerospace vehicles, you actually have body fixed sensor or actuators, and these can give you 3 degrees of control of the rotational motion, and usually just one translational degree of freedom is directly controlled. So that is underactuated, but it's known that we can go from we can go from point A to point B. Path planning is possible with that kind of actuation. More importantly, there are actuator constraints, and that can restrict achievable state trajectories. So these are things that if you factor in during the design, then it's better than trying to redesign or change your design on the fly after you have designed a control scheme or an estimation scheme. So I'm depicting quadrotor UAVs here, rotorcraft unmanned aerial vehicles. And here I talk about dynamic uncertainties, and that is due to external environmental conditions like atmospheric turbulence. And in this case, we have actually found that active disturbance rejection control using some of our schemes, which are geometric control schemes and estimation schemes, works very well. And I'll actually talk about that later. So this is where I have just some simulation results here on relative motion formation control for multiple vehicles. And this is through onboard sensors. This is just a decentralized formation control with collision avoidance using a stable and robust control scheme. So added to that is as I mentioned, we have sensor constraints. And for this three-vehicle spacecraft problem, we looked at particular sensor constraints where we are just looking at the direction of one spacecraft from another, but each spacecraft, we assume, can measure its own orientation, which are depicted by these three axes, red, blue, green. So these are the initial configurations, relative configurations, and then they come around to form a formation, triangle formation, as shown here. So I don't go into the details of the schemes, but that's something that we have done in the past. So getting into the path planning problem, this is a situation where we have a guidance for a vehicle that's like a quadrotor UAV with a fixed thrust direction. And we have 3 degrees of rotational degrees of freedom controlled directly with the 4 thrusters. And you can generate a sequence of waypoints as shown here in an inertial frame. So I denote these waypoints by G1, G2, G3. That is to denote that they are encapsulating both the position of the base body as well as the orientation. So G is basically the pose, which takes into account both the position and the orientation. And we specify some waypoints in pose, and then we have a motion planning scheme to execute that. So at a high level, the kinematics for a single rigid body is given in this SE3 framework for the special Euclidean group of three-dimensional rotations and translations. This is the framework that we use. So G denotes our pose, psi denotes our velocities in the body frame. So this is angular velocity in the body frame, and nu is the translational velocity in the body frame. Often you can express the translational velocity in inertial frame, and for that we use v instead of nu, and you'll find that v is what occurs in the dynamics equation here. And so this would be for something flying in air where you have a gravity direction is denoted by E3, so which is just 0, 0, 1. So that's the vector 0, 0, 1 column vector. And phi d is our disturbance from the unknown disturbance force, and tau d is our unknown disturbance torque. And we have a control torque, tau c, and a control thrust force, fc. And with this, we can actually generate a trajectory given some waypoints. So this was actually part of a project that we did 7 or 8 years ago now, maybe 2018, 2020. It ended around 2020, just around the time that COVID hit. So this was an interesting, we actually did not fly it outdoors, Joe. I show how the trajectory is generated. And this is a location in Syracuse, downtown Syracuse, that we used as a sort of simulation test bed where we generated this trajectory from start to finish, going around these towers, considering a building inspection situation from the outside. And this was actually done, the waypoints were designed using a reinforcement learning scheme, but it was outside the loop, because it took a lot of time to do that. So I would definitely not put it inside the loop. And then once the position waypoints were generated, we then generated a position trajectory using nothing but LQR. And the LQR model was basically a fourth order integrator model. Fourth order because we know that the snap, which is the fourth derivative of the position, is directly related to the torque, the control torque applied to the rigid body. So when we translate from the position trajectory to the desired attitude trajectory, then it makes things easier. So obstacle avoidance would still be needed, and we do that using artificial potentials, but of a different kind. These artificial potentials are based on what we call polar Morse functions. So they have a minimal set of critical points in this nonlinear state space. And that's the best you can do, actually, with continuous feedback control. So we then, of course, generate the trajectory. It's based on a best known dynamics model, but then the control scheme takes care of the disturbance rejection. So we have a trajectory generation, then we have the motion estimation, and then, of course, the feedback control scheme. So that completes the entire loop. So the trajectory planning, as we found, can be done on board, and we use learning algorithms to generate 3D waypoints, trajectories. But of course, for real-time onboard implementation, we put that outside the loop, and then we use sensors to go through those generated waypoints using GPS for outdoor flight. We didn't actually test it in that area, and at that time we were warned by the police, so we actually settled on an area where we got permission to do this in a field, generate this trajectory and waypoint. And this was done, and we actually also did this later in simulation, not in the actual outdoor flight. But in simulation, we also added a pointing direction constraint, and that was interesting. So let's see if this, I don't know okay. So if I have time, I'll just share this trajectory generation, and I think I have more videos, but I may not have time to go over those. So this is the situation where we actually have, so this is where it goes through those waypoints, and you'll see that the red line aligns with or red axis aligns with the direction that we want it to point. And curiously, it makes these S-shaped curves. That's actually the trajectory, that's position trajectory that's generated by the LQR. And it ends at each location, you'll see that the pointing direction is satisfied. So going back to my presentation, so this, okay, so now I'm going to switch gears, and I'm talking about motion estimation. So actually, for motion estimation, for attitude estimation, it turned out to be quite easy and very easily implementable in hardware. Translating from theory to practice was easy. We came up with this interesting relation between what is known as Waba's problem in attitude determination, has been around since the space age started. And then we generalized it to Lagrangian, and an artificial Lagrangian use artificial kinetic energy like term and artificial potential energy term. We found that Waba's problem, the minimizing of this residual, is actually, it leads to a Morse function, a polar Morse function.
Amit, we don't see the slides right now.
So. Oh, sorry. Somehow forgot to switch.
Now we can see it. Thank you.
Thank you. Yeah, so as I was saying, this is the situation that we found that Wawa's problem in attitude determination is actually with judicious choice of the weights. And if you have independent direction measurements, then so the directions measured are denoted as U, and the M just denotes measured. And the corresponding inertial known vectors are E. So Waba's problem is very, very common for satellite attitude determination, where you look up at a star field, and then you match it. So your sensor, a star tracker, let's say, looks at the stars, and then you match it with a database of the known stars in the sky, and those inertial directions that are known are matched with what the sensor is seeing. And this problem then is how do you determine the attitude between those matched vectors? And that's actually Wawa's problem. So this can be actually, if you represent it using the trace inner product, and that's what these triangle brackets represent, then it turns out to be polar Morse function that is continuous and twice differentiable. And you can use that as part of your potential energy when you construct a Lagrangian, and then the residual in the angular velocity estimation between the residual, meaning the difference between the measured and the estimated, is used in this quadratic function, which is a kinetic energy-like quantity. And then we have a Lagrangian composed of that. And then if we introduce an additional Rayleigh dissipation term and apply Lagrange D'Alembert principle, then actually we end up getting what I call the variational attitude estimation scheme. And this is going to give you a stable estimation scheme that is robust to uncertainties in the dynamics and measurement noise, because it's actually model independent. So it's a data-driven sort of estimation scheme, of course. It does not depend on the model because you do not know what the dynamics model is. You do not know what the inertia, for example, inertia parameters are, the mass of the body, etc. So this can be discretized using the discrete Lagrange D'Alembert principle. So this is discrete geometric mechanics. I don't go into the details again, just giving a very high level description here. And we compared this with, at that time, with some schemes that are still kind of used. This is a filtering scheme from 2013 called the game filter, geometric approximate minimum energy. So this is like a second order. The extended Kalman filter is first order. So this is kind of a second order Kalman filter. And it's based on work that was done in the 1960s by a person at UCLA, trying to get higher order estimation schemes, optimal estimation schemes by for nonlinear systems by generalizing the Kalman filtering formulation. And then we compared it with the MEKF, the multiplicative extended Kalman filter, and this constant gain observer. All estimators, we simulated it, and then we also implemented it on a smartphone. And all estimators start with identical initial estimates, estimation error, identical sensor measurement, noise, and sample rate. So this was interesting. It was actually reported in the ICRA in 2015. So we show the principal rotation angle in the estimation error. So we start off with very bad estimate. Initial condition is way off. As you can see, it's like 1.2 radians almost. And then all these schemes are shown to converge when your MEKF and the game filter, these are making the correct assumptions on the sensor noise and sensor properties, basically the amplitude of noise, etc. However, if I do not change the filter gains, and now I have a better sensor, my noise levels are now less. What happens is interesting. The variational estimation scheme, which is this red, does some weird transients. It does have some weird transients, but it does converge after a period in this scenario. However, the second order, the game filter, and the first order extended Kalman filter, multiplicative extended Kalman filter, they blow up after a few milliseconds actually, and they don't continue after that. And the constant gain observer keeps oscillating. It never converges. So if I zoom into the first few milliseconds or centiseconds here, you'll see what is happening is that the MEKF and the game just give up after a few, like 4 sample, I'm assuming a constant sampling of 0.01 seconds. So after the first 4 samples, they just give up. I mean, they blow up. So that's expected because it was kind of counterintuitive at first, but then we realized that actually if the sensor is better than what was thought when you designed it, and that's where optimality, as I say, is only with respect to whatever index and whatever assumptions you made. So if those assumptions are wrong, then you can have unstable behavior. So near optimality is what you get with these kinds of filters, and near optimal does not guarantee stability. So experimentally, we validated this also using at that time, 2014. I don't know if this is going to work or not, but this was actually did not seem to work, but this was actually implemented on a 2014 Google Pixel, and it did work out fine. So in summary, it worked out without needing to be retuned. Every time you change sensor does not mean that you need to retune. It'll throw the estimation scheme off a little. It'll have transients, as we saw, but it's still going to converge. And then we extended this. We made a finite time stable version of this, which was continuous, uniformly continuous. We use Holder continuous finite time stable schemes, which are actually implementable, and they're uniformly continuous. They're not like sliding mode type observers or control schemes. So it works out very well. We found that in 2014, 2015. However, pose estimation is a whole different ballgame, and we are only now realizing it. And our pose estimation schemes, and I'm just going to go over this fast in the time given, so I know that I'm behind. So this is actually using the same sort of idea. Here now for pose estimation, you have point clouds. So these could be from LiDAR or depth cameras. It could even come from sonar or radar. But point clouds are then, you find centroids for the point clouds. And then assuming that you have perfect measurements, this is how the centroid of the point cloud that you have in the inertial frame and the point cloud that you measure in the sensor frame, this is how they are related. And R is the rotation, B is the translation of the sensor with respect to an inertial frame. So at least one 3D point needs to be measured to estimate the position, and you need 3 others to estimate the orientation, but those could be direction measurements. And so we have, for measurements, we can have some linear filtering to remove noise from the sensor frame. And then we relate the vehicle translational and rotational velocities to these measurements without actually directly measuring them. And this was interesting. So we have again, we create the potential energy and kinetic energy, a Lagrangian from that. We apply the Lagrange-D'Alembert principle, and we get numerical simulations. And then we also implemented this using two types of sensors. Intel RealSense series sensor, which also has active depth detection, and the Z2I sensor, which is a depth camera. So we are using it still. And these are the simulation results that I have based on different initial errors and measurement noise bounds. So we look at first the perfect case in case one, where there is no measurement noise. And then this is the case where we have measurement noise and we lose a full measurement. So we lose measurement of certain vectors during periods. And you can see that during those periods, it's kind of diverging. But when you retain full measurements, like at least 4 vectors measured, then you come back to your zero pose error. So one disadvantage. The advantages are it does not require a dynamics model, can be implemented in poorly known environments, can be implemented with commercial off-the-shelf sensors with low power requirements, and can be used to estimate relative motion states also between multiple vehicles. And it is robust and stable. Disadvantage is it does not really have, or it does not predict error margins or bounds on velocity estimates, because we are actually estimating the velocity indirectly from the points measured, unless it's coupled with model-based observers. And there is a recent work that is under review which extends this to finite time stable pose estimation, which is more robust to the sensor noise and dynamic uncertainties. And this can be used in even underwater vehicles would probably need sonar, but definitely for UAVs and spacecraft. So I'm going to skip this slide because I think I'm just 12 minutes on the left, and I have a lot of slides left. So I'm going to switch gears again. And now I'm going to go into the robustness aspect with our schemes for active disturbance rejection control, which use disturbance observers or extended state observers. And in the dynamics equation for the rigid body vehicle, we have the disturbance force and disturbance torque in this equation too. So this is what we are trying to estimate without, of course, directly measuring them. We have states that we measure, or in the case of point cloud measurements, they are external measurements that we translate to state estimates. So the process is known as active disturbance rejection control. As some of you may be aware, this is has been around in the robust control community for some time. And we obtained both discrete and continuous time disturbance observers and continuous time extended state observers. And this provides the ability to learn unknown dynamics in real time. And in this scenario, we actually design a disturbance observer of this form, where this is starting with an initial estimate, and this function that you have here is it could be a function that gives you asymptotic convergence, or it could be a function that gives you Holder continuous finite time stable convergence. And you can design it to ensure some ultimate bound on the disturbance estimation error. So you can have a set tolerance, and this, of course, requires one thing that I highlight here, a caveat, is that it requires knowledge of bounds on the rate of change of the disturbance inputs. Interestingly, of course, if the disturbance input is constant, then we estimate it perfectly. But if we have dynamic disturbance input, which changes with time, then the bound that we settle into would depend on how fast it changes. So usually disturbance inputs have low frequency content in real life, so we are saved by that. And it's not really restrictive for the type of disturbance and extended state observers that we designed. The interesting thing that I'd just like to point out, one bullet point here, is that these disturbance observers can be used to design a stable data-driven control scheme. It could be a black box entirely, or in more generally, it's just a gray box, because for robotic vehicles, you usually have some physics-based model very well known, and then you have the uncertainties. So but it could be used in practice and in theory for a complete black box. And that actually has not been done in practice, but in theory, we have shown that. In practice, of course, we tested it on uh, um, a UAV, quadrotor UAV, in front of a fan array wind tunnel that threw three-dimensional turbulent airflow at the UAV. And then we have some simulation results here. And I'm just going to play this. I know that somehow my embedded in the LaTeX Beamer is not working, so I'll switch again to play this video. Let me switch back. So what I wanted to mention here is that you saw that this was on a harness because we don't want it to fall and break apart when we hit it with the turbulence. Now, when the turbulence was started, this is with an exponentially stable extended state observer. When the fan array wind tunnel was started, which is not visible in that video, unfortunately. But there are more videos actually on this that we have on my website, on my lab website, where when we hit it with the turbulence, you see that it suddenly went up and came down, but that was because of the sudden wind gust that hit it. And then but then it recovers and it maintains the hovering pose while while the turbulence is hitting it. So that was actually a quick recovery in that sense. So that's what we implemented um, in our experiments. So I return to this 3D pose estimation here, again changing tracks, but this is where we have actually now implemented some of this. And we have, again, I don't want to go out and then start these, but this is actually implement. Let me just try to do this again. Um, so, uh, So this is actually where we have our 3D pose estimation scheme. So we have a version of it um, that's in a patent, but this is let me just switch again to this video where we we actually implemented this in using um, GPU and the Intel sensor first, and then we implemented it using the depth camera sensor. So we have a version now with the depth camera sensor. Actually, I'm probably late now, but I had some more slides that I got rid of, which are on this and it is a copy of slides that I presented at the 2024 CDC in December, last December, where we implement this using the depth camera sensor. So again, I'm going to switch gears quickly and talk about a different problem. This is small body proximity operations. This is actually an interesting dynamics problem that I tackled a long time back. This was when I was in New Mexico, but it's still a problem that's close to my heart. And I'm not sure if you, okay. So, um, so this is actually looking at coupled translational and rotational dynamics. When you look at a spacecraft around a planet-sized object, this is a table that shows you like the orders of magnitude of translational and rotational kinetic energies. When you're orbiting a large asteroid, you can see that there is still a large magnitude difference. So gravity, as I mentioned, does induce some coupling, and that coupling becomes more and more pronounced as the orders of magnitudes of translational and rotational kinetic energies become closer and closer. So when these become differ by 2 orders of magnitude or less, then you just cannot ignore that anymore. So for small body missions, we found that if we have a point mass trajectory that says it goes this way, and even with a very basic ellipsoidal model of an asteroid the size of Itokawa, which is a small asteroid, um, uh, we find that there is significant difference because of the coupling, or maybe you can call it a disturbance in the translational trajectory induced by the rotational motion. So even if you did not have any initial angular velocities to start with, just because of gravity, there is some gravity gradient torque on the body. And unless it's a perfect sphere, spherically distributed mass. And in that case, you'll find that the coupling itself induces this rotational motion, and the trajectories are very different. So one is not impacting, the other is actually impacting the surface of this body. And of course, the initial translational speed that we started with is 5% more than circular speed at a certain altitude. And this is approximately the rotation period for Itokawa, which is a uniform rotating body, and it has a constant major axis rotation. And actually, for tumbling bodies, that's even worse. So I think I skipped a slide here. So yeah, this is for Bennu. And we see that Bennu, it was theorized that you could have solar radiation pressure stabilize an orbit, which was called terminator frozen orbit. But this was with a point mass model. When we include the rigid body effects and gravitational orbit attitude coupling, which this term was actually coined later by these authors in 2019, then we find that if we include that, then actually solar radiation can strip the spacecraft away from the body, and you can see that it's moving away. What was interesting is that we also generated landing trajectories with no thrusting. And this was a visiting scholar that I had, and he did a large part of the work. This was pre-COVID. It was published in 2019. And this was a visiting scholar from China who I worked with. He generated a lot of good results using our models and the gravitational orbit attitude coupling phenomena. So this was actually some work that we did then. I think I'm not doing very well on time right now. So I'll just skip this part. So this is actually a novel variational speed control moment gyroscope design. So I'm switching between topics, I know, randomly, but this is just a interesting dynamics problem again, where we designed variable speed control moment gyroscopes. Now these are attitude actuators used in spacecraft. Normal design is this, where you have a gimbal axis and you have a rotor, and the rotor's center line coincides with the gimbal axis. Here, we deliberately introduced an offset, and the dynamics is very much more complex, but then you actually get some additional control authority. And this has a lot of applications, but we have not really explored all those applications, although we have a patent on this design. It's probably the smallest control moment gyroscope that we have come up with, or anybody has come up with, in fact, because as you see, it fits in the palm of hand. So actually, the student who worked with me on this particular design started the company that was mentioned, Acrobatics. I was just, a minor player in that. He now has a different base. I'm not associated with that company anymore, but he makes autonomous snow removal robots, calls it Snowbotics. So it's still in existence, but I'm not associated with it anymore. Anyways, just to quickly end my talk, I think I have a few more slides. So this is what I see as outstanding challenges in um, autonomy for aerospace vehicles, in general vehicles, robotic vehicles. It could also be underwater or surface water or ground vehicles. Guaranteeing stable convergence with onboard constraints. Um, Perception still remains a problem, although we are looking at a case where we have now onboard really computationally very efficient pose estimation schemes. They're not SLAM schemes, they're not mapping the environment, but they at least let the vehicle know where it is in relation to the surrounding 3D environment, which is important, especially for collision avoidance. And guaranteeing robustness of navigation and feedback control schemes to unknown or unmodeled inputs, which we have handled, I think, very well. Now, humans in the autonomy loop is something that others are working at. I'm very tangentially aware of that. I have a person who wants to use my lab. He's one of our former students who has a project with the Air Force, I believe. He started his own small company, STTR project that uses LLMs to command drones. So again, as long as that is outside my feedback loop, my navigation and control loop, I'm happy with that. Inside the loop, I'll be very worried. So that's what that's what, that's how I'm tangentially associated with that. But I believe that we have overcome many of the constraints for stable motion estimation in real time. It's still a challenge, but it's actually the most pressing challenge. The data-enabled control approaches, real-time learning, robust control, those I think are more doable, and we have done that. It took a long time for us to actually get the pose estimation working. Translating research to practice, of course, building collaborative tries. This is always easier said than done. I try to, as I tell my students, it's good theory that leads to good practice, but I'm not the type of person who is very well connected. And sometimes when I talk to people and I talk to them about geometric mechanics and geometric control and estimation, they probably think that this is too theoretical to be of any use in practice, which is why actually I had a visitor from Cambridge today earlier in my lab, and he was talking about how they use LLMs for multiple robots, ground robots, and commanding them. He was showing his work there. And then he remarked about how these schemes were very efficient, rejecting disturbances using neural networks. And at the end, we got around to discussing, and he said that they have real world problems where in the real world, there is logistics problems like in warehouses where they don't care about optimality. And he was told that when he went to demonstrate his robots in a warehouse where they are using autonomous robots for or grocery picking, apparently, in a place in England, some company in the UK that does that for, it's basically your grocery. Instead of you going to the grocery, these warehouse stores all the grocery items and the robots do the picking. If you do the order online and then it gets put into a cart and then packaged and sent to you. So that was interesting. So they have to do it without collision and without multiple robots working together. So that was something that they use text to control and LLMs, but I'm not really very much into that yet. I'm just tangentially learning about that stuff. Future research, of course, I have, this is actually part of a pending, pending proposal, but because of some things that I couldn't manage in time, I just decided to include it. This is kind of like a digital twin concept where I have a surrogate model based on our observers, extended state observer kind of ideology, but this is hybrid physics-informed reduced order model that we have, and then it's basically a gray box. Maybe if you have a physics-based model for the F, the D is unknown, and then you have some control scheme, and then you learn about this F and or you learn about this D, and then that gets into an uncertainty quantification using adaptive Monte Carlo schemes, non-Gaussian uncertainty, maybe plus outputs of interest, and then you have a prediction error between what you predict for these quantities and what you get from the adaptive Monte Carlo. And then that gets into this differential model, and then that gets fed back to improve our model here, especially the D. And so we learn about the system over time. So this is like a digital twin concept. So with that, I come to my last slide. I know that I'm like 10 minutes over the limit, but this, I just have acknowledgements to my students and past postdocs. I'll mention that some of them here, Reza, he's in Blue Origin now. He was a student and then a postdoc. Jan is in Raytheon. Asan was my first student, and he is in Rivian autonomous cars. So Sashi is actually still the owner of Acrobatics. Yeah, so my current students are Curtis, Neon, and Nazanin. And I had another student who could not come and is not likely to, or had now, because I just can't get him because of the current situation. I don't think I'll be able to get a student from China anymore. But you are all aware of the situation, but that's just. So this is some collaborators I mentioned here and funding agencies. This is my cover article from the IEEE Control Systems magazine way back in June 2011, and it describes why continuous feedback cannot achieve global asymptotic stability for a rigid body. Now, this is something that Ricardo knows as well because he used hybrid control schemes in his research, in his PhD research also, to overcome this obstacle. So that's all for that I have for today. I'll be happy to take questions at this point. I know that Ricardo had a class, he told me. But if there are others questions, I'll be happy to take them now.
Yeah, Ricardo just had to step out. So do you guys have any questions here?
I have a question. In your for the variational estimator that you mentioned, you said it was model free, and you said it was robust. So how do you characterize robustness without notions like ISS, for example, where you need the model?
Yeah, so robustness in this sense, I meant robustness to the sensor noise. And as I mentioned early on, these are deterministic schemes. So they are, of course, the good thing about that is they are computationally efficient, much more efficient than probably like the second order Kalman filtering type of scheme that I mentioned. And also they're robust in the sense that if you change the sensor, if you swap the sensor, it'll still work, as I showed. And it might have transients, but it'll still converge. It's still going to show stable behavior. Yeah, of course, the dynamics model-free part is also in the sense of the dynamics. The kinematics is, of course, known for a rigid body, but the dynamics, I don't assume any knowledge of mass and inertia parameters, of forces acting on the vehicle, etc. Yeah.
Any other questions? No, I believe Piyush and you and Himadri will be meeting. Amit, do you still have time to stick around for the next 30 minutes or so? For a couple one-on-ones with Piyush and Himadri?
Sure. Yeah, I can.
Or past time, so just making sure that you can stick around a little bit
Yeah.
longer. Okay, great. Any final questions in the room? All right, well, let's thank Amit again.
Thank you. It was a pleasure.
Yeah, thanks so much, Amit. Yeah, so you hang on this Zoom line. Do you guys want to take it? This room may be needed at some point. I don't know if someone might be coming in. So do you guys want to take it from the lab?
Yeah, sure.
Otherwise, you're welcome to keep using it here, but if another group has information and
okay.
pictures, so it's your call.
Okay.
Okay. Great. Well, Amit, if you need to take a little bio break, I think Piyush, are you up first or?
We'll do it together.
Oh, okay. They're gonna do it together. Okay, great. Yeah. So just sit tight. Do you want to do it here? Or you can go to the lab.
We'll go to the.
We are going back.
Okay, great. All right. So they're running over to the lab. They'll be right on. Amit, if you need to use the restroom or anything, just keep the Zoom open and they'll join shortly.
No, I'm fine, actually.
Okay, great. Well, I'm going to log this off, but yeah, keep the Zoom open and Piyush and Madri will be on in just a moment. So
Sure.
thank you again.
Sure.
All right, Piyush, Amit, I'm going to set you as the host, just a heads up, and then I'll be hopping out. So.
Okay, that's fine.